Taylor and Maclaurin series. In the previous section, we were able to find power series representation for a certain restricted class of functions. And to be more precise, this class of function consists of functions that are in one way or another related to the following function that you see on the screen. Right? So this function, we found that this the power series representation of this is the geometric series whose terms are this guy to power n, correct? And that geometric series is convergent to this one, to this function, as long as this guy is an absolute value less than 1. This is what we found in the previous section, or this was the backbone of the previous section. In this section, we're gonna, however, investigate more general problems. To be more precise, we're gonna try to answer the following two questions. We're gonna ask which functions have power series representations, and how can we find such representations? Okay. To get started, let's suppose that f actually has a power series representation, and let's say that this power series is centered at A in this context. So what I'm saying is, let's suppose that equation 1 holds, okay? And let's say it holds for, or let's take the radius of convergence to be r. In other words, we're saying that this one holds, this equality holds, for any x in between a minus r and a plus r, okay? Let's take a number. I mean, what's the question here? The question here is to find or to determine all these coefficients, the Cn's, right? If we find them, then we know exactly how to represent a function that can be represented by a power series. Okay. All right. Let's take a number in this neighborhood of A. Let's take A itself. Certainly A lives here. Let's take A itself, and let's replace x by A. I can replace x by A because I can replace x by any number that lives here, and A lives here. So let's replace x by A. This becomes f of A, right? This becomes A, and so on, correct? So we can read it as follows. F of A is equal to C0 plus everything here is 0, right? A minus A is 0. 0 times C1 is 0. So every term here is 0. So what the value of the right-hand side becomes is just C0. So C0 is f of A. Okay, and this is what I wrote here. So C0 must be f of A. Okay. Moving on. Let me erase just all these A's here. Okay, so moving on. Let's recall the theorem of the main theorem of the previous section. Remember this theorem? It said a power series is infinitely differentiable, right? And you can actually differentiate it term by term, right? So it's infinitely differentiable in the interior of its interval of convergence. And you can actually do the derivative exactly as you were to do the derivative of a polynomial. So appealing to that theorem, I'm gonna differentiate this equation, or I'm gonna differentiate the two sides of the equation, equation 1. The left side becomes f prime, and the right side is gonna become 0, right? This is a constant. C1 times the derivative of this, which is 1, so C1, we get C1, plus let's differentiate this guy, it becomes just chain rule here, 2C2x minus A, you get this, correct? And so on and so forth. And the radius of convergence remains the same. If you start with the radius of convergence to be r, you're going to end up having the same radius of convergence. Okay? All right. And now, how about doing the same thing? Let's choose an x that lives in this neighborhood of A. How about replacing choosing x to be A itself? Certainly A is here again. F prime of A becomes C1 plus 2C2 times x minus A, but x is replaced by A this time, so it becomes A minus A, and A minus A is 0, right? Plus 3 times C3, that quantity to power 2, and I'm replacing that x by A. and so on and so forth. So what can you say then? You can say that all these are 0. The only thing that survives on the right side is C1. So C1 must be f prime of A. Okay, and this is this result. And we're going to keep doing the same thing. Okay, so we're going to keep doing the same thing. By this, I mean I'm going to keep applying that theorem of the previous section. So I'm going to keep differentiating. I'm going to differentiate one more time. I'm going to get f double prime. So I'm looking at equation 2, differentiating both sides of equation 2. I'm going to get f double prime on the left side. And on the right side, I'm differentiating term by term because of that theorem we just alluded to. So the derivative of this is 0. The derivative of this is 2c2. Derivative of this is 6 or 2 times 3 c3 x minus a, and so on and so forth. And again, if you differentiate, don't forget the radius of convergence remains the same. So let's choose again x to be a. So let's choose a special x that lives here. We're choosing a. As such, we get f double prime of a. Now you got, you know the drill. So that whole thing is gonna disappear. The only thing that remains alive on the right side is 2c2. So f double prime of a is gonna be 2c2. And if you continue doing this over and over, you're gonna get, I hope you start seeing. So the next time you're gonna get 2 times 3, which is 3 factorial, right? And so on and so forth. And the general one is gonna look like this. This notation, remember what this notation means? This is the nth derivative of f at a is gonna be n factorial times cn. So it's this is, in this case, this is when n is 2, right? This is when n is 1. So overall, or in general, that's the formula. And this is true for any n that's, and I mean, this means, this guy means, this is my notation for n union 0. What does this mean again? Boldface n stands for the set of all natural numbers. And I'm taking that set to be, I mean, the union was 0. So n, I mean, boldface n sub 0 means all the non-negative integers. Okay. All right. So we get this formula. And here we are adopting the following convention, or the following conventions. We're saying that if n is 0, we're allowing n to be 0. If n is 0, we're talking about the 0th derivative of the function. And what's the 0th derivative of the function? So it's natural to think about it as just the function itself. And as such, we get the 0th derivative of f, which is f of a, is equal to 0 factorial, and we're adopting that 0 factorial is 1, times c0. So we get c0 to be f of a, and this was found before, right? It's right there. Okay. All right. As such, what's the cn then? The cn is equal to the nth derivative of f at the point a divided by n factorial, and this is true for any n that's non-negative integer. Okay. So we just proved the following theorem. If you suppose that the function f, again, I cannot emphasize that enough that I'm talking about this assumption first. If you suppose that f has a power series expansion at a, which means you're supposing that this holds in some neighborhood of a, then those cn's must be this quotient, the nth derivative, I mean, cn must be the nth derivative of f at a divided by n factorial. Okay? So as such, if you take cn, replace it here, you get this property f of x is equal to sigma. I'm replacing cn by what they are. So the nth derivative of f at a divided by n factorial times x minus a to power n. Right? And we're still under this assumption that this holds for any choice of x in the neighborhood of A which has radius r. Okay. And this guy is what's called Taylor series of the function f at A, or Taylor series of the function f centered at A. Centered. Let's be here. Okay. All right. So this is what we refer to as the Taylor series of the function f, because f is the ingredient here. It's the function involved at A, because we're talking about the point A here. Okay. So they are part of the name. They are part of the name. Okay. So again, this result holds as long as you're assuming that f has a power series expansion. Okay. Not every function has the following property, as you're going to see shortly. All right. By the way, Taylor published. His first name was Brooke. He was an English mathematician. He published this result in 1715 in his book. Okay. Now, for the special case when A is 0, so when you replace A by 0, what do we get? We get f of x equals summation the nth derivative of f at 0 divided by n factorial x minus 0, so x to power n. We get this. That series, which is a particular case of Taylor series, is referred to as Maclaurin series, and Maclaurin is a proper name. His first name was Colin, and he was a Scottish mathematician. So even though this is a particular case of Taylor, but Maclaurin made it famous when he replaced A by 0. He made it famous in his 1742 book, and it's got the name in honor of him. Okay. All right. So let's summarize what we have. We've shown that if you suppose that the function f has a power series representation centered at A, then f is equal to its to the sum of its Taylor series, right? Then f is going to be equal to the sum of its Taylor series. Very good. But there are functions, there exist at least one function that's not equal to the sum of its Taylor series. For instance, consider the following function. Consider this function, f of x equals e to power minus 1 over x squared if x is not 0, and 0 otherwise. If you try to find f prime at 0, if you differentiate this function at 0, by definition, what does it mean? This is just definition here, right? By definition, it's the limit as x goes to 0 of f of x minus f of 0 divided by x minus 0, this difference quotient, is equal to, if you replace what f of x is and what f of 0 is, you get this. And now if you use Hopital for this, this is of the form what? If you rewrite it as such, this is which indeterminate form? This is of the form infinity over infinity, right? If you use Hopital for this, I'll spare you the details. The answer should be at the end 0. Okay. Again, we're not supposed to write this. Please, this is technically not correct to write it, but this is what's going on our mind, right? So at the end of the day, we get 0. So f prime of 0 is 0. In a similar fashion, we may use the definition of derivative and L'Hopital's rule to show that the nth derivative of f at 0 for any n actually is also 0. And as such, the Taylor series, and as a matter of fact, it's the Maclaurin series expansion for f, is just 0, consists entirely of 0 terms, right? Why? Why? Because this guy is 0. In our context, this guy would be 0. And if this guy is 0, you are summing, you have a countable sum of zeros, and that's 0, right? So this side becomes 0 is equal to this function, and certainly this function is not 0, right? Certainly this function is not entirely 0. It's only 0 at when x is 0. So this is an example where you have a function which is not equal to to the Taylor series, to its Taylor series. Okay, except when x is 0, obviously. Okay. All right. So please do not think that any function can be written as such. Okay. But obviously, functions do have Taylor series centered at a point, but that series may not converge to the function. That's what we're saying. This equality, I'm talking about the equality, this may not happen all the time. Okay. All right. Example 1. Find the Maclaurin series of the function f of x equals ex and its radius of convergence. So what's the Maclaurin series of f? Well, it looks like this, right? By definition. Correct? So I'm talking about this right here. All right, let me erase this guy. So I'm talking about this guy, right? Okay, so obviously the function f is infinitely differentiable here. It's ex. If you differentiate it, you get it back. Okay, so what's this then? What's this? No matter how many times you differentiate the function f, it's always itself, correct? And if you evaluate it at 0, you get 1. Does it make sense? So since the nth derivative of f at 0 is 1 for all n and n not, so non-negative integer. So this becomes sigma, or the series, the power series, 1 over n factorial x to power n. Okay? Or you can write it as xn divided by n factorial. Let's write it this way. Okay? All right. So they also asked the radius of convergence. They want to find the radius of convergence of this one. Well, for the radius of convergence, how about we go for the ratio test? So applying the ratio test, what do we get? If you call this guy an, so the ratio test says evaluate the absolute value of this quotient, right? So evaluate this and let n go to infinity. If you get something smaller than 1, then you have absolutely convergent series. Otherwise, not otherwise, bigger than 1 you have divergence, and equal to 1 the test does not apply, right? Okay, so this is equal to the absolute value of x to power n plus 1 divided by n plus 1 factorial divided by an. By now you know the drill, so we get n factorial divided by xn, correct? So I'm dividing by an, which means I'm multiplying by the reciprocal of an, which means that guy. Now if you simplify, you get n plus 1 downstairs. Why? Because this guy is equal to n factorial times n plus 1, correct? We talked about this before. And now if you simplify by n factorial, then you get that n plus 1 downstairs. And now if you simplify by x here, oh, by the way, I dropped the bars because n plus 1 is a positive entity. And upstairs you have n plus 1 copies of x. Simplified by n copies of x, you get simply just x upstairs with the absolute value. Okay? And no matter what x is, this goes to 0 as n goes to infinity. Make sense? Even when x is 0, if x is 0, this whole thing is 0 anyway. So, and if x is non-zero, this becomes a non-zero constant over something that blows up. So certainly it goes to 0. Okay. So what can you say then? So no matter, this is for all x. This is for all x. So no matter what x is, that limit is smaller than 1, right? No matter what x is, that limit is smaller than 1. So by the ratio test, we get that the radius of convergence is infinity, right? So no matter what x is, this limit is less than 1. It's actually 0, correct? As such, by the ratio test, so by the ratio test, so technically this is what I'm using, the ratio test. I'm going to erase this part. So by the ratio test, I get that the series, which is xn divided by n factorial, is absolutely convergent, and hence is convergent for all x. That is to say, the radius of convergence is infinity. So what can we say? What's the conclusion that we can draw at this point? We can say the following. If the function ex has a power series expansion at 0, then ex is gonna be this guy, right? Correct? So the conclusion is, let me write it in blue. So conclusion, up to this point, if, and again, I'm gonna write if in red because we don't know that this is the case, right? So if the function ex has a power series expansion, at 0, then ex is equal to the summation, this one, right? And this is for all x, because the radius of convergence is infinity. But the question becomes, how can we actually make sure that ex does have a power series expansion? Correct? The next theorem is going to actually address this question. It reads as follows. Let little r be a positive fixed number. Okay, so let r be a positive fixed number. If there exists a number m, positive, such that for any non-negative integer, the following happens. And what's the following? It's the absolute value of the nth derivative of f is bounded above by this number m, an absolute value, for any x, right? So it's bounded above in that neighborhood of a, of radius little r that's just fixed here. Okay, so let's read this one more time. What's the requirement for the conclusion, the desired conclusion? What's the desired conclusion here? Let's take a look. Then the function is gonna equal its Taylor series. Okay, so this is the question that we just asked here. How do we actually know that ex does have a power series expansion? Because we know if it does, then it equals this series, right? The question is how do I know that this happens? Or how do I make sure? Maybe it doesn't. So let's read this theorem again because it's going to address that question. Let's take a number r that's positive and fixed. Let's fix it. If you can find a universal m, and by universal I mean it's independent of x, it's a universal m. If you can find a bound, which is a universal bound that doesn't depend on x, that bounds the absolute value of the nth derivative of the function from above on the interval a minus r and a plus r, if such a thing happens, then what you want what you want happens. And what you want is the function is going to equal its Taylor series centered at a on that interval, right? And here I should say that r is should be positive for sure, but it should not exceed how about being smaller than the radius of convergence? The radius of convergence of what? The radius of convergence of the Taylor series. Okay, so this is like a provision to this assumption here. Okay, because the series, the Taylor series is not going to converge if you give me an r bigger than this number, right? It's radius of convergence. All right, so this is like a provision. This is an implicit thing. Okay, so if you are able to bound the function, all the derivatives of the function f from above by a universal number m, by universal I mean it's independent of the choice of x, on that neighborhood of a, then the function is going to equal its Taylor series expansion centered at a on that neighborhood. Okay, the proof of this is not that hard. I'm gonna eliminate it just because I'm gonna eliminate it. However, if you want me to do it, I'll be very happy, obviously, to do it. Just write for me, and I'll send it to you. But I'm gonna eliminate it here because I just don't want the video to be too long. It's already gonna be long, but just to cut it a little shorter. Okay. All right. And another thing to highlight here is that this is a sufficient condition. What you see here, let me highlight it for you. What you see here is a sufficient condition, but it's not necessary, meaning a function f may equal its Taylor series centered at a without this happening. Okay, so it's a sufficient condition. It forces the desired conclusion, but it's not necessary. Okay. All right, so back to example 2, which is gonna refer us to the previous example. Prove that EX actually is equal to its Maclaurin series. So prove that EX is actually equal to this. So in other words, prove that this assumption, the if part, is it is the case that EX has a power series expansion at 0. So by this theorem, it suffices to show this, right? It suffices to show this. That's what I want to show. So I want to take an r positive, and I would like to find this m. That's what I want to find, such that this inequality holds, right? Such that this inequality holds. Make sense? So the question is, what's that guy? That's the thing that I want to find, if I'm able to find it. Okay, so let r be a number that's fixed. Let me write it here. So let r, let r be a positive number, be fixed. Then what can you say about the nth derivative of f at x? Well, the function in our case is ex. Don't forget the parentheses. So the function in our case, that's f of x, and the derivative of this, no matter what n is, the nth derivative of this is itself, right? So that's gonna be itself. You can erase the bars because ex is never less than 0. It's never 0. It's always positive, right? So this guy is EX. And now if you choose an X, to be as such, right? I'm rewriting this thing for my context. Who's A in my context? I'm talking about Maclaurin series, so the center is 0, right? So this becomes absolute value of x minus 0 less than r, right? So if you take such an x, this means that x in absolute value is less than r, which means x is less than r, right? So as such, this implies that x is less than r, correct? Do you agree with me? If the absolute value of x is less than r, so in particular, x is smaller than r, right? Because what does this mean? What does absolute value of x being smaller than r? It means that x is between minus r and r. So that's what I'm saying. It follows that x is smaller than r. Okay? And if x is smaller than r, the exponential function is an increasing function, right? Ex is an increasing function. So that's gonna force ex to be smaller than er. Do you agree with me? Because the exponential function is an increasing function, so ex is going to be smaller than er. So what can we say then? This guy is going to be smaller. That's a different color. Is going to be smaller than er for any x as such. Okay? And take a look at er. Does it depend on x? Does this value here depend on x? Do you see x in it? This is independent of x. This only depends on r, which was fixed before the choice of x, right? So remember, look at the timing here. You fix r, then you want to find m, so that for all x this happens. So the x comes after, right? The x comes after you choose r and you know the existence of m. Then x is allowed to be chosen. So er again, does it depend on x? This guy? This doesn't depend on x. I see nowhere x in this expression. It only depends on r, which is a number fixed way ahead of the time I chose x, right? Okay, so that's the bound m. I can treat this as the bound m. Certainly this is a positive number, right? So that's the bound m that I'm talking about. That's the m. That's the m in the theorem. Okay, so what can we say then? I was able to find a bound, a uniform bound, for the nth derivative of the function f on that neighborhood. So therefore, what's the conclusion? By this theorem, we can say that the function f, which is ex, is equal to its Taylor series, which is Maclaurin series because I'm talking about the center to be A. So centered at 0, so Maclaurin series, on the interval x minus a less an absolute value less than r. Correct? So how about I continue here? I know I'm kind of like jumping around, but just excuse me just this time. I'm gonna write right here. Okay, so I'm gonna put dot. Actually, I'm gonna write below. I'm gonna write right here. So these dot, I'm picking them up here. So thus, for any number r that we fix, right? For any number that we choose, the function, based on the theorem, the function is going to be at the end equal to the sum of its Taylor series by the previous theorem. So thus, for any fixed number r, we found that the nth derivative, let's do it in stages. the nth derivative of f at the point x is less than or equal to ER, which is the m. That's what I'm going to choose as m, correct? And this is for any x in the neighborhood of A centered at R, that fixed number R. So by the previous theorem, this is where the previous theorem kicks in. So by previous theorem, we can conclude that the series, the Maclaurin series, which is xn over n factorial, right, is equal to the function ex, where does this happen? It happens for all x in that neighborhood, right? So this happens for all x in that neighborhood, a minus r, a plus r. Make sense? And this is, don't forget, this is for all number r. Okay, so far so good. Okay, so what's next? That series, we said it's gonna match ex if it has a power series expansion at 0 for all x in R. Well, here so far what we have is they do match as long as you give me x in between a minus r and a plus r. I would like to say for all x in R, in boldface R, all real numbers. Well, don't forget, little r is arbitrarily chosen. No matter what you choose r to be, then that's gonna happen. So I'm gonna write and then explain that I can conclude, and here I'm gonna say, how about I label it by an exclamation mark, just to indicate to you that something delicate is going on here. The series xn over n factorial is gonna equal ex for all x in R, boldface R. And let's explain why. Let's suppose that, all right, one more time, let me help you understand one more time this thing. So for any real number r that you choose that's positive, we know that this guy and this guy are gonna be equal for all x in between a minus this number and a plus this number, correct? But this choice r is arbitrary. You can choose any r you want, but once you fix it, that happens. What I'm claiming is that this happens for all real numbers, okay? Because look, how about you? How do you convince the audience that this is the case? Suppose that this doesn't happen somewhere for some x, okay? If this doesn't happen for some x, okay, so say, I'm gonna write it just quickly here. So say this guy is not this guy for some x. How about we call it x naught? What can we say then? According to our previous analysis, by the way, here a is 0, right? So let me fix it just now. This guy is 0, this guy is 0, this guy is 0, right? Because we're talking about the Maclaurin series, so that a is 0. All right, so what can we say then? Or what do we have? We know that if you choose an r, then these two are the same for any x between minus r and r, correct? I'm supposing that they're not the same for some x naught. Okay, I'm supposing they're not the same for some x naught. I'm gonna choose that R to be, so choose R to be the absolute value of x not plus 1. How about that choice for R? Certainly this number is bigger than 0, it's at least 1, right? So certainly such an R can be chosen to replace this R here. Based on the previous analysis, I know that this guy and this guy must be the same for any choice of x in between minus R and plus R, and that R I'm talking about is this R, right? So based on this, I can say that these guys are the same is equal to ex for all x, so for all x in between minus, right, minus R and plus R. What's minus R in this case? That's the R I'm talking about. So minus absolute value of x naught minus 1 and absolute value of x naught plus 1, right? That's the minus R and that's the plus R. Okay, so they are the same for any choice of x as long as you give me an x here. Well, x0, x naught lives here, no? X naught lives here. Do you believe that? So x naught is a guy that lives here. Why? Why is that? Can you clarify it yourself? Well, x naught is always a bound for the opposite of its absolute value, right? And it's always bounded above by its own absolute value. Do you agree with this? So because of that, if you subtract 1 from this guy, you're decreasing the bound, so x naught becomes bigger than that guy. And if you increase the bound by 1, x0 is going to be smaller than the absolute value of x0 plus 1. So x0 certainly lives here. So I can take x to be x0 and put it here and get this equality, correct? Because this equality, according to the analysis we have, this equality holds for any x between those guys, x0 in particular. So if you replace x by x0, that equality holds, but this is a contradiction to what we just said. Make sense? So such a thing can't happen then, right? Such a thing can't happen. And what we said, that's the delicate part, which is the explanation part. And what we said then is going to be true. So those two things are the same. So meaning the function ex and its Maclaurin series, they're equal for any choice of x. Make sense? So I'm going to keep this as small discussion here. I'm going to save it for you in the notes. Okay. But this is the delicate part, correct? Okay. All right, so long story short, ex is equal to its own Maclaurin series. Okay. All right, so then we can say, so let's read these two lines. So thus ex is equal to its own Maclaurin series for any x in R. This is what we just said. In particular, when x is 1 is a real number, so replace x by 1, you get e to power 1, which is e is equal to 1 over n factorial, that series of the terms which look like 1 over n factorial, right? So you get this e written as this infinite series. Okay, so e is the summation of 1 over n factorial, and n starts at 0. Okay. All right, example 3. Find the Taylor series for the function f, which is ex, the same function we've been dealing with, but now this time, not the Maclaurin series, which means the center is not 0, this time is centered at 2, and show that it represents ex for all x in R. Okay. I'm going to leave it as an exercise, but I'm going to give you the key ingredients. So how do you start this thing? So you have f of x is equal to ex, which means the nth derivative of f is going to be ex for any x and for any n, right? So if you replace If you replace x by 2, that's gonna be like this, correct? So what's then the Taylor series expansion of ex at centered at a equals 2 is gonna be, so the Taylor series would be the summation. It starts at 0. This is what the Taylor series expansion is of the function f at a, which is 2 in this case, by definition. So it's f, the nth derivative of f at 2 divided by n factorial times x minus a to power n, right? Agree with this? And this is for any x in a neighborhood of 2. We'll see what the neighborhood is later. And what is that? This guy is e squared, right? This guy is e squared. So this becomes, actually I'm going to highlight it. This is e squared based on what we just discussed above, right here. Okay, and we get this. So the Taylor series expansion of the function f at a equals 2 is going to be like this, summation, and that series starts at 0, e squared over n factorial x minus 2 to power n. Okay, and I'm gonna leave it to you as an exercise again. What's the radius of convergence here? It's gonna be very similar discussion as before. Okay, the Taylor series expansion is gonna be is gonna have the radius of convergence to be infinity again. Okay, how do you do it? Ratio test. So ratio test is gonna tell us that the radius of convergence is gonna be plus infinity. Okay, please complete the details. I'm just giving you, because this is the same work as we just did above, right? So we found at the time that we were dealing with just the center to be 0. Okay, it's the same, but this is just to redo it in some sense. Okay, so that series is convergent for all x. That series is convergent for all x. What they want is they want us to show that this series, because it's convergent, it's converging somewhere, and that limit actually is this function ex. Okay, this function ex. Well, we know that this series is the Taylor series expansion of ex. The only thing that remains to show is that the function and its Taylor series match, right? The only thing that remains to show is that the function, which is ex in this case, and the Taylor series expansion at 2 are equal. Okay, so how about you find, we have a sufficient condition for that to happen. How about you find this bound M? Over here at the time we found ER to be the bound, R being that fixed number, if you remember. And in this case, it's gonna be, instead of ER, where did this R come from again? It came from the fact that x in absolute value is smaller than R, right? Which means x is smaller than R. And hence we found the bound M. In our context now, what do we have? We're gonna have the absolute value of x minus 2, because our center is 2 this time. Absolute value of x minus 2 less than R, which means x minus 2 is less than R. So instead of x minus 0 less than R, is going to be x minus 2 less than R, which means x is less than R plus 2, right? So x is going to be less than R plus the center. The center here was 0. Now it's 2, so R plus 2. And as such, ex, because the exponential function of base e is an increasing function, ex is going to be less than e to power R plus 2. For any such an x. So the bound would be e to power r plus 2. Okay, so you get to see that or in general, if you don't take 2, if you take a, the bound here is going to be e to power, or the bound may be chosen to be e to power r plus a. Okay, so my point here is the same game, just redo it to learn it, and then what? And then we get to that same point. We get to that same point, right? So we get that the series the Taylor series of the function centered at 2 is equal to ex for any x in between 2 minus r and 2 plus r, right? Over there it's going to be 2 minus r, 2 plus r. And you're going to use the same argument, the same reasoning, not the same argument, the same reasoning to actually find that they are equal, the function and its own Taylor series, expansion centered at 2 in our context, for any choice of x. Okay, so as such, you answer the question. So I'm gonna put here, complete this, please. But keep in mind that I just gave you all the details, okay? It's the same as before, as we said. Very good. Let's keep going. Example 4. Find the Maclaurin series for sine x and prove that it represents sine x for all x and r. Okay, so now we're gonna, let me do it on a new page. This is example 4. Okay, so here we're gonna find the Taylor series expansion, or the Maclaurin series expansion for sine. So the function in our context is sine of x. Okay, so what's f of 0? It's 0. Now we're gonna go to the first derivative, f prime of x. I'm trying to find all the Cn's in the Taylor series expansion, right? And each Cn, if you remember, looks like the nth derivative of the function at the center, which is 0 in this case, divided by n factorial, right? Okay, so I want to find the derivatives. F prime, I want to try to find a pattern, obviously. F prime is derivative of sine, which is cosine, which means f prime of 0 is equal to 1. And if you differentiate f prime another time, or if you differentiate f another time, so you're differentiating f prime, you get f double prime, which is negative sine of x, and the value is going to be 0 if you evaluate f double prime at 0. And the third derivative of f is going to be negative cosine of x, which means the third derivative of f at 0 is going to be negative 1, sorry, negative 1. Let me erase this, negative 1. And then the fourth derivative is going to put you back at sine, right? Because the derivative of cosine is negative sine, so negative the negative is going to be plus, so sine of x. And then the fourth derivative of f evaluated at 0 is going to be sine of 0, which is 0. So we're back here. We're back here. Correct? So it looks like the derivatives repeat in a cycle of 4, right? So this process is cyclic of order 4. Okay? So this process repeat in a cycle of 4. Right? Cycle of 4 stages. So we can write the Maclaurin series as follows. So the Maclaurin series would be what? So the first one, when n is 0, this would be when n is 0, so the 0th derivative, which is the function itself, at 0, so this is 0. So when n is 0, we get 0. When n is 1, we get 1 over n factorial, right? So 1 over n factorial, and n is 1, so 1 over 1, x to power 1, so we get x. Correct? Now, when n is 2, that guy is 0, the second derivative is 0. When n is 3, I'm gonna have upstairs -1 divided by 3 factorial x to power 3. So I'm gonna get minus x cubed divided by 3 factorial, and that thing is gonna repeat again. It's gonna repeat again. So we go back. Now it's gonna repeat after 4 times. So one first derivative plus 4 more gives me fifth derivative, right? So at the fifth derivative, I'm gonna have 1 as this guy. So it's gonna be 1 over n factorial, 5 factorial x to power 5. So it's gonna be plus x5 divided by 5 factorial. And then the 6 is gonna be 0 because it's similar to the second. And the third, or the seventh, is gonna be similar to the third. So it's gonna be -1 over 7 factorial times x to power 7. Okay? And so on, plus dot dot dot. What's the general recipe for this? Well, this is an alternating series, right? So this is an alternating series. So it's gonna have this component -1. Let's figure out the exponent. If you put n, this n starts at 0, so it's even, so that's good, right? So, and then times what? Times these odd powers, so they're gonna look like x to power 2n plus 1. Let's check this. When n is 0, this becomes 1, so we get that guy. When n is 1, this becomes 3, correct? And so on. So this looks good. And downstairs is the same guy as the exponent, but factorial. So it's going to be 2n plus 1 factorial. Okay. All right, so this is the Maclaurin series for sine. Right there. Okay. And what's the question now? They want us to prove that this represents sine for all x. Okay. So what does it mean? What does it mean? If you go back to that theorem, in order for a function to equal its Taylor series centered at A, in this case the Maclaurin series because the center is A, it suffices to find a uniform bound. This is a sufficient condition again. A uniform bound for its nth derivatives. Okay? And this is easier than the previous one, right? So this is easier than the previous one because the function and its derivative are either sine or cosine or some or change of sign of the trig functions, correct? What I'm saying is the following. Since the nth derivative of f at x is either plus or minus sine or plus or minus cosine, you agree with this? So these are the options for the nth derivative of f. What can be that m in the theorem? Well, the absolute value of such a function is always bounded above by 1, right? You can take m to be 1 in our context, correct? So we may choose m to be 1. M of what? Let's be clear on this. So m of the theorem, right? Of the theorem above. Makes sense? So as such, we get that actually i.e. the nth derivative of f at the point x in absolute value is less than or equal to 1, and this is for any x in absolute value minus 0, which is x, okay, less than r, and this is for any r positive, right, no matter what you choose for r. Same discussion, that's gonna force the sine function to equal its Maclaurin series, right, which we found it to be -1 to power n x to n plus 1 divided this is an x here, 2n plus 1 factorial, right? This guy. Because this happens for any r, as we discussed for the exponential function, this is going to be also for any x and boldface r. Makes sense? Okay. Sine is an odd function, remember, and I hope you see that its Maclaurin series expansion at 0 is it's just picking up those odd powers, right? Just to reinforce that the function is odd. Okay. All right. Example 5. This was example 4. Example 5. We want to find the Maclaurin series for cosine and show that it represents the cosine function for all x and r. So it's the same problem, but now we have cosine instead of sine. So you can treat it exactly as before, or you can capitalize on the result of example 4. And but what do I mean by capitalizing? Well, let's zoom in to cram it here. What do I mean by capitalizing? I mean the following. I know that cosine of x is the derivative of sine of x, right? I know this. Agree with me? On the other hand, I know that sine, based on the previous example, I know that sine has this power series expansion. This is the Maclaurin series for sine. So we had -1 to power n, x to power those odd powers, x to power 2n plus 1 divided by 2n plus 1 factorial. Correct? And the previous section, we know how to differentiate a power series. This is a power series centered at 0. So we know how to differentiate a power series term by term, right? So term by term. So this is theorem and previous section. I'm going to write term by term for you to remember. Okay. And that the derivative of this is going to be, I mean, that function is going to be differentiable for all r, right? Why? Because it's going to have the same, not for all r, for all x and r, because it's going to have the same radius of convergence as the original one, which is sine, right? Which is that series. Correct? So they're going to share the same radius of convergence, which is infinity in this case. So for any x and r, we're going to get at the end that this new series expansion is going to converge, and hence it's going to equal to cosine. Make sense? All right, and what's that result? Let's differentiate this term by term. We get summation. Let's go back to blue. So we get summation. -1 to power n, right? If you differentiate this, what do you get? X to power 2n plus 1. If you differentiate it, you get 2n plus 1 times x to power 2n plus 1 minus 1, which is 2n, divided by this 2n plus 1 factorial, right? Correct? And that's going to start at 0. Make sense? Because it's going to start at 0 because the first term is not a constant. The first term is x. Remember, the first term and the expansion, the Maclaurin series expansion for sine, it was x. Okay, when n is 0, this guy is x, right? So the first term, when you differentiate, you don't get 0, so you don't shift that index. Okay, and now if you simplify, by 2n plus 1, that guy is gonna cancel. All right, let's be clear about this. What is this piece? This is 2n factorial times 2n plus 1, right? Agree with that? So if you simplify by 2n plus 1 upstairs, you can simplify by this guy. And then I'm gonna only have 2n factorial downstairs. So what do I get? I get that this is equal to the summation of -1 to power n x to power 2n divided by 2n factorial, okay, which is the Maclaurin series for cosine. And keep in mind that, as we said, since the derivative of that power series is going to have the same radius of convergence, then that series is going to also be convergent for all x and r, right? For all x and r, by that theorem, the term-by-term thing, right? I mean, that theorem of the previous section. So for all x and r, and as such, this series is going to equal that cosine function for all x and r. Okay? Make sense? All right, moving on. Find the Maclaurin series for the function f of x equals x times cosine of x. So in example 5, we just developed the Maclaurin series expansion for cosine, right? And now let's capitalize on that to develop the Maclaurin series for f of x, for this function. We know that cosine of x, we found that this is equal to sigma -1 to power n x to power 2n divided by 2n factorial, correct? And this is for all x. This is for all x. So what we have here is x times cosine of x. So how about we multiply by x both sides? Correct, we get that. And this is equal to, this x is independent of this index n, so I can bring it inside. It's a constant with respect to n. I can bring it inside that discussion here, that term, and get, or inside the sum, and get what? -1 to power n times x to power 2n plus 1, right? If you multiply x to power 2n by x, you get x to power 2n plus 1 divided by 2n factorial. Okay? Alright, so this is not that bad. So the Maclaurin series expansion for this function, x cosine is equal to that series, right? And this is for any x in R, right? Because the Maclaurin series expansion for cosine is equal to cosine for any x in R, multiplying it by this polynomial. This x is not going to change anything. So this is for all x in R, right? Okay. All right, so example 7. Find the Maclaurin series for f of x equals 1 plus x to power k, where k is in R. Okay, let me go to a new page. Let me go to this page and let's start this example. This is example 7. So our function here is 1 plus x to power k, and k is any real number, right? K is any real number. And we want to find the Maclaurin series for this function. Okay, so let's start by evaluating this function at 0, because Maclaurin series is Taylor series centered at 0. So let's start by finding f of 0. F of 0 is going to be what? It's going to be 1, right? Okay, let's differentiate the function f of x. If we differentiate the function f of x, what do we get? We get k times 1 plus x to power k minus 1. And as such, you differentiate, or you evaluate f prime at 0. You get what? You get k. Agree with this? All right, and let's keep going. Let's try to find a pattern. That's what I mean. So let's differentiate again. We get k times k minus 1 times 1 plus x to power k minus 2, and that's gonna tell me that f double prime at 0 is what? K times k minus 1, correct? Okay. F triple prime at x now is going to be k minus 1 times k minus 2 times 1 plus x to power k minus 2 minus 1, so k minus 3. And that's gonna entail that f triple prime at 0 is, that guy is 1, so k times k minus 1 times k minus 2. Okay, and I hope you see the general formula. So in general, the nth derivative of x is gonna be k times k minus 1 times k minus 2 times dot 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 all the way to, so for the third derivative we stopped at k minus 2, for the second derivative we stopped at k minus 1, for the nth derivative I'm gonna stop at k minus what? So when I had the third derivative I stopped at k minus the previous number, so 2. So here I'm gonna stop at the previous number, which is n minus 1, right? Okay, makes sense. And what's k minus n plus n minus 1? Isn't it k minus n plus 1 if you destroy the parentheses? Okay. And how about immediately evaluating it at 0? That's gonna be this, right? So technically I should write 1 plus x to the power k minus n, right? You know what? Why not? Let's do it. So k minus n as a power here, and then this entails that the nth derivative evaluated at 0 is equal to k times k minus 1 times dot 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 all the way to k minus n plus 1. Okay, and this is for all n, this is for all n and n naught, which is the non-negative integers. All right, so we know the general or the nth derivative, no matter what n is, the nth derivative of the function at 0. So we're ready to write the Maclaurin series expansion. So thus the Maclaurin series of f of x, which is 1 plus x to the power k, is equal to, the formula is sigma n starts at 0 to infinity, the nth derivative of f at 0 over n factorial xn, right? Now we know what these guys are. They are these pieces. So I get summation starts at 0, k times k minus 1 times k minus 2 all the way to k minus n plus 1 all over n factorial times xn. Yes? This series has a name actually. This series is called the Binomial Series. Okay, how about I write it for you? So this is called the Binomial Series. So the Binomial Series. Okay. And just as a point of reference, look, you see the k, you see this k here? K is a real number, right? So if that k is actually a natural number, so if it's a positive integer, what does it mean? It means at some point, if you keep differentiating, at some point you're gonna get 0, right? So at some point one of these guys would be 0 if k is a natural number. At some point this guy, one of those guys becomes 0, and as such the series is going to become simply a polynomial. Okay, it's going to be simply a polynomial. And in fact, if you've seen it before, um, whenever k is a natural number, um, so since it's going to be a polynomial, as we said, so it's going to be it's going to terminate, and at the end of the day, it's going to reduce to what if you've seen it before, it's the ordinary binomial theorem. Okay. All right. I just thought I would just point this out. Another thing is that quotient here has also a name. So this guy has also a name, and it's called the binomial coefficient. The binomial coefficient. And it has a notation, and probably you've seen it before. It's k choose n. Okay. This is the universal notation for this quotient. Anyway. Okay, so what was the question again? Find the Maclaurin series for the function 1 plus x to the power k. We found it. It's right there. It's the binomial series. And how about we study the convergence of this? How about we run the ratio test? Actually, how about you run the ratio test? So do the following. Run the ratio test. Okay. And let me just tell you what you should get. an plus 1 over an. That's gonna be equal to, actually it's gonna converge, right? It's gonna converge in this context to the absolute value of x as n goes to infinity. Okay. So once you do so, you can infer then by the ratio test. What do you infer? That if this guy is less than 1, you get convergence, and if it's bigger than 1, you get divergence, right? So the binomial series, so you infer that the binomial series converges if the absolute value is of x bigger than 1, smaller than 1, right? Smaller than 1, and it diverges if the absolute value of x is superior than 1. Obviously at 1 and negative 1, or when the absolute value is equal to 1, we cannot say anything because it depends on k, right? It depends on k. What k is? That k, that exponent. Okay. All right. Let's go to the next page. So as it turns out, this function 1 plus x to the power k is actually equal to the sum of its Maclaurin series for any k, as long as x in the absolute value is less than 1. Okay, so what I'm saying is that the function is equal to its to the sum of its Maclaurin series. And how did we use to show that they are the same? Remember that theorem, this one, that we introduced earlier? We used to find this universal bound M, right? Unfortunately, in this context, this bound M is very hard to be found. However, since this is not an if and only if statement, right? The good news is this is not an if and only if statement, which means we may be able to find that the function and the sum of its Taylor series to be equal without checking this, without having to check that this is gonna hold, without checking that this requirement is holding. That's my point. Okay, because it's not an if and only if statement, which means we may be able to find a different condition under which this conclusion follows. Okay, let me show you. Let me show you in this case what would be an easier way to show that this equality is true, which means on one side the function and on the other side it's the sum of its Maclaurin series or Taylor series centered at 0. A way to do it is if you call this guy function g, let's say, if you call this function g, how about you show by differentiating this series, you show that g prime of x is actually equal to k times g of x divided by 1 plus x. And this is for all x in absolute value less than 1. Okay? So again, call this function g of x, call this guy g of x, because that guy converges as long as x is in an absolute value less than 1, right? So call it g of x for those x's, and show that g prime is going to be like this. Once you differentiate, you get this. Show this. And once you show this, part 2, if you call the function h of x to equal, so if you call h of x to equal 1 plus x to power minus k g of x, show that the derivative of this is 0. Show that the derivative of this is 0 for all x. Okay, it's not hard, just do it. I'm breaking down the process. Okay, so do part 1, then go to part 2, and then guess what part 3 is. Once you show that h prime is 0, which means h is a constant, right? This function is a constant on this interval, -1, 1, right? So again, this is for all x in absolute value less than 1. If you remember one exercise in Calc 1, which relies on the mean value theorem, if you remember, if the function is differentiable on an interval and its derivative is actually 0 on that interval, then it must be a constant on that interval, right? So that's what's going on here. So if h prime is 0 on this interval, -1, 1, this is -1, 1 here, then the function h is going to be a constant, which means that this guy is a constant, which means that gx is equal to c divided by, or c times 1 plus x to power k. Okay? If you call that constant c, and then if you replace x by a suitable number, then you figure out what this constant is, and at the end of the day, you're going to find that g of x is actually equal to this. The constant is going to be 1, right? Okay, so part 3, just deduce. Deduce the equality. What equality I'm talking about? This equality, right? Okay, so this is a little exercise for you to do. So this is a little exercise for you to do to actually show this equality. Okay. Why I'm giving you this exercise? Because as I said, the previous technology, by this I mean that theorem here, this upper bound is hard to be found. So I'm trying to show you a different way to actually show that the function and its Taylor series are equal to each other. Okay, and this is the way I broke down the steps. All right, example 8. Find the Maclaurin series for the function f of x equals 1 over square root of 4 minus x and its radius of convergence. Okay, so well, f of x is equal to 1 over square root of 4 minus x. I can push out a 4 and factor, right? I can push out a 4 and factor. So I can write 2 times 1 minus x over 4 to power half. Agree with this? And this is the same as 1 over 2 times 1 minus x over 4 to power negative half. Right? Now I'm gonna use, now this is of the form 1 plus something to power k, this guy. 1 plus something to power k. So I'm gonna use the binomial series here. So I'm gonna use the binomial series, with what? Who's the k? Who's the k here? Is negative half, right? K to be negative half. And who's the x over here? It's negative x over 4, right? So, and x to be negative x over 4. So that's what I'm going to be doing here in this step. And if you do so, what do we get? What do we get? We get half, that half is this guy, times the summation. I'm reading now, I'm reading this part. N starts at 0 to infinity, right? K choose n. What's k again? Negative half. Negative half choose n minus x over 4 to power n. Make sense? Okay. And since the binomials, so this is the Maclaurin series for this. This is the Maclaurin series for this function f. So since the Maclaurin series, since g of x, the Maclaurin series for 1 plus x to power k, right, which is the binomial series, converges for all x in absolute value less than 1, we're going to infer that this series here is going to converge for all x and for all x so that the absolute value of negative x over 4 is less than 1, right? So the x and the binomial series is our negative x over 4, right? So since the binomial series converges when the absolute value of its variable is less than 1, we infer that the series, this series, okay, how about we label this whole thing actually? How about we call this equation star? Okay, so that the series in star, and what do I mean by star? I mean this series here, right? Converges when the absolute value of its variable, which is negative x over 4 to power 1, right? So that guy is less than 1. Okay, and what does this mean? This means that absolute value of x should be less than 4. Make sense? So what's the radius of convergence? Because they care about the radius of convergence. The radius of convergence is, this is centered at 0 because it's Maclaurin series, so x minus 0 less than 4, so the radius of convergence is 4, right? So radius of convergence is just the 4. Make sense? Okay. Let me draw some separation here. Okay. All right, example 9. Find the sum of the series 1 over 1 times 2 minus 1 over 2 times 2 squared plus etc. Looks like this, 1 over n 1 over n times 2 to power n, right? Agree with this? Okay. Well, they gave you a hint. The hint is, recall from the previous section, we derived this result at the time, that ln of 1 plus x is this summation. And this is true for any x between minus 1 and 1. Okay, so how do we do this? Please obviously think about it on your own. And the way I'm going to approach it is, I'm going to rewrite this as follows. That's equal to sigma, n starts at 1 to infinity minus 1 to power n minus 1, right? It's alternating. When n is 1, this is going to be even, so that's going to be plus 1 over n times 2 to power n. Do you agree with me? So when n is 1, that's going to be plus here. That's going to be 1 over 2, right? 1 over 1 times 2. When n is 2, that's going to be negative. That's going to be negative 1. 1 over 2 times 2 squared, and so on. Okay? So that looks good. And this is equal to sigma. Again, I'm trying to approach it this way, right? Sigma n starts at 1 minus 1 to power n minus 1. I can think about this as 1 over 2 to power n divided by n. Okay, that puts me in this context. Yes? Now use the hint. Now use the hint here. Use the hint to get what? What does the hint tell me? It tells me that no matter what x you choose here, as long as x is between minus 1 and 1, possibly 1, this guy is equal to ln of 1 plus x. Who's the guy here? Clearly it should be half, right? It should be half. So that's going to be ln of 1 plus half, which is ln of 3 halves. Make sense? So that sum that you see here, that series, it's convergent, and the value is ln of 3 over 2. It sums up to ln of 3 over 2. Okay? All right. Example 10. Use the Maclaurin series expansion for ex to evaluate the limit as x goes to 0 of this function if it exists. Right? So this is an indeterminate form of the form 0 over 0. Right? If you place x by 0, you get 0 upstairs, 0 downstairs. So L'Hopital handles it for sure because the functions are differentiable. So, but we're not going to do it using L'Hopital. I'm going to do it using Maclaurin series as they requested. Okay, so let's do example 10 over here. So if we use or using the Maclaurin series, for ex, we know it from an earlier work, right? We've done that. What did we find at the time? We found that ex is equal to sigma xn over n factorial. Remember this? And this is for all x and r, right? So we're gonna use this, and if you use it, by the way, what is that guy? If you take a moment to write this out, what is that guy? When n is 0, you get 1, right? And when n is 1, you get x over 1, so x. When x is 2, you get x squared over 2 factorial, plus when n is 3, x3 over 3 factorial, right? Plus etc. And as we said, this is for all x and r. All right. So using this, we get to the limit. What's the limit? The limit as x goes to 0 of ex minus 1 minus x over x squared would be equal to limit as x goes to 0 over x squared. Downstairs is x squared. Look upstairs. Ex minus 1 minus x. This is ex. It's 1 plus x plus all the rest, right? So ex minus 1 minus x would start here, right? Would start here. So this would be x2 over 2 factorial plus x3 over 3 factorial plus x4 over 4 factorial, right? Plus dot dot dot. Why again? Because ex is that series, and ex minus 1 minus x, so ex minus 1 minus x would be this guy, right? So you're just adding to this convergence series negative 1, the quantity negative 1 minus x. They cancel these guys, and you start here, right? Okay, and what is this limit? What's that limit? If you simplify now by x squared, that limit becomes that limit becomes 1 over 2 factorial, right? 1 over 2 factorial plus, if you simplify by x squared over x squared is 1, so 1 half. 2 factorial is 2, plus x cubed divided by x is x over 3 factorial plus what? Plus x squared over 4 factorial, right? Correct? And so on. What's the next one? x5 over 5 factorial divided by x squared. This would be x cubed over 5 factorial, right? And so on and so forth. And what's that? As x goes to 0, that's going to be 1 over 2 factorial, which is 1 half. And this is because here I'm using the continuity of the power series. Remember, power series are differentiable. And they are differentiable in the interior of the interval of convergence. This guy here, it's convergent for all x, remember? For all x. So as such, this function is going to be continuous because it's differentiable for all x. And as such, the limit as x goes to 0 would be just evaluating this guy at 0. And if you evaluate this guy at 0, you get half, right? By the continuity of the power series. Make sense? Remember the continuity of a function, f of a continuity at a number, right? I'm using continuity at 0 here, so remember f is continuous at a if and only if, by definition, f of a is equal to the limit as x goes to a of f of x, right? That's what I'm talking about. That's what I'm talking about. And here, that's the function, and a is 0, right? Okay. All right. Example 11. Find the first 3 non-zero terms in the Maclaurin series ex sine x and tangent x. So that's example 11. Part 1. Let's use, so we have the function ex sine x, right? So we want to find the Maclaurin series expansion for, not the Maclaurin, sorry, the first 3 non-zero terms in the Maclaurin series for ex sine x. Okay, so let's use the Maclaurin series for each one. So ex sine x is equal to, again, here there's something I'll talk about at the end, why I can do what I'm doing. So I'm multiplying two functions. I'm gonna use the power series expansion for each one, but please be careful here. Just I'll tell you why I'm using it shortly. So what's the power series expansion of ex? Wasn't it 1 plus not the Maclaurin series for ex, 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. Okay, and what's the power series, or what's the Maclaurin series for sine? We found it to be 1, not 1, x minus x cubed over 3 factorial plus x 5 over 5 factorial, right? Minus etc. Correct? So we found it to be something like this. Okay, what's the question? They want to find the first 3 non-zero terms in the Maclaurin series for ex sine x. What are those first 3 non-zero terms? Well, in this product, what's the lowest degree you can get? Certainly I will not get a constant, because there's no 2 entities you multiply here to get a constant. The lowest I can get is power 1, right? Power 1, just the x guy. Okay, so, and how do I get the power 1? I get it when you multiply 1 with x, right? If you multiply 1 with x, you get the power 1. Make sense? So, and that's the only power 1 term that you can get. There's no other combination that does the job, right? Okay, because if you multiply 1 with x with any other, it becomes more than 1. If you multiply x with any 1 here, the lowest you can get is 2. So that guy, that multiplication is the only guy allowing me to get a term of power 1. Now what's this guy then? That's x, correct? So the power series expansion for the Maclaurin series for ex sine x starts with x. That's the first non-zero term. Now the second, what's the second? So this is of power 1. The second is gonna be of power 2 if it's non-zero. And do we have any non-zero term that's of power 2? Yeah, I see it. When you multiply x over 1 with x, correct? That's the only time you get. If you multiply this term with this term, that's the only guy that allows you to get a term with the second degree. Any other combination doesn't make it, right? So that's gonna be so plus, what's the result? If you multiply x over 1, which is x times x, you get x squared, right? Okay, so the greens with the greens. And now the next term would be power 3, right? And do we get any power 3? Yeah, if you multiply the x2 with the x, you get power 3, right? But is it the only one? If you multiply this guy with this guy, you get power 3, but is it the only one? If you multiply the one with this term, you also get power 3. Make sense? If you multiply this with this guy, you also get the power 3. Okay? Let me label them for you. So these guys are the 3 guy, the degree 3 guys. These guys are, or this guy is the degree 2 guy. And this guy is the degree 1 guy, right? Okay, so we're talking about the degree 3. So the only way I get degree 3 is when I multiply 1 with x cubed over 3 with a negative sign, and when I multiply x2 over 2 with x. That's the only way I get power 3. Is there any other way? I don't see anything, right? Okay, so what do I get then? I get the power 3 guy. What's the coefficient of that guy? If you multiply 1 with negative 1 over 3 factorial, you get minus 1 over 3 factorial. And if you multiply 1 over 2 factorial with 1, you get just 1 over 2 factorial, right? Make sense? Plus the rest. We don't care about the rest because they're asking only about the first 3 non-zero terms in the Maclaurin series, and these are the first 3 non-zero terms. Okay, what's that guy? So we get x plus x squared. If you want to simplify, how much is this? 3 factorial is 6, and 2 factorial is 2, so this becomes 1/2 minus 1 over 6. 1/2 minus 1 over 6 is 1/3, right? Plus etc. Okay, makes sense. So here one more time, let me talk a little bit about this. So even though we didn't justify the formal manipulations of this product here, but it is legitimate, and by being legitimate, I'm referring to the following. So there is a theorem that states, which is beyond the course. I'm not gonna prove it, but it states the following, just quickly. If you have two functions, f of x, which is a series Cn xn, and another function g of x to be sigma bn xn, say, with both of which converge for all x less than a number r, okay? And if you take And if you take the product between these two functions as if they were polynomials, like we dealt with here, right? If you take the product between those two functions, those two series, as if they were polynomials, then the resulting series is going to converge for all such an x, for such x, and it's going to represent the product f times g. Okay, so if you take these two series and you multiply them as if they were polynomials, like we did exactly here, then the resulting series is going to be convergent for all such an x, an absolute value less than this r, and it's going to represent the product f times g. Okay, so I'm not going to write all the details, but that's the story behind that. This is why we were able to actually apply it. Okay, it's that theorem that I just alluded to. All right, the second part of this problem. So the second part of this problem, they gave us tangent x, right? And they want us to find the first three non-zero terms in the Maclaurin series of tangent x. Well, tangent x is sine x over cosine x, correct? Makes sense? And I know the Maclaurin series of sine, and I know the Maclaurin series of cosine, right? There's also a theorem similar to the one I just mentioned for this equality here, that for division, we require the first entity here not to be zero in the denominator. The first, so in the Maclaurin series of cosine, or in the Maclaurin series of the denominator, we require the first term not to be zero. And what's the first term in cosine? The first term in the Maclaurin series of cosine, it's 1, right? It's 1. So certainly it's not 0. So if you treat this as if they were two polynomials, the series, if you treat it as if they were polynomials and you do long division as usual, then the resulting series is going to converge for sufficiently small number x, and it's going to converge to this quotient. Okay? Anyway, so we're going to treat the power series or the Maclaurin series of sine and cosine as if they were polynomials, and we're going to do long division to find the first three non-zero terms in the Maclaurin series of tangent. Okay, what's the power series or the Maclaurin series for sine? Let's start at x minus x cubed over 3 factorial plus x5 over 5 factorial minus etc. divided by, I'm gonna stop at 3 because they said they just want the first three terms, right? Divided by 1 minus x squared over 2 factorial plus x4 over 4 factorial, right? Minus etc. This is for cosine. Okay, and let's do long division, or a procedure like the long division. So I have x minus x cubed over 3 factorial plus x5 over 5 factorial, etc. And here I have 1 minus x squared over 2 factorial plus x4 over 4 factorial minus etc. Okay. By the way, 4 factorial, how about we replace those guys? What's 4 factorial? It's 24, right? What's 2 factorial? It's 2. 3 factorial is 6. And 5 factorial is 120, right? Okay. All right. So the question is, what should we multiply? What should we multiply 1 to get x? Let's multiply it by x. If you do so, you get x times 1, which is x, minus x cubed over 2, and plus x to power 5 over 24. Okay. All right. Obviously plus or minus, etc. I'm gonna, again, as I mentioned, I'm gonna stop after 3 terms because they only care about the first 3 non-zero terms, and then we subtract. And what do we get? What do we get? X minus x is 0. Negative x cubed over 6 plus x cubed over 2. So it's negative 1/6 plus 1/2. And what's negative 1/6 plus 1/2 is 1/3, right? We just did it above. X cubed. And then 1 over 20 for, oh, this is x5, this is x4. Okay, so is it x5? Oh, this is x5. Okay, my bad. This is x5, right? Because x times x4 is x5. Probably discovered this before. Okay. Then we get what? So 1 over 20 minus 1 over 24. 1 over 20 minus 1 over 24. What is it? Minus 1 over 30. X to the power 5. Okay. Etc. Anyway, so the algebra is annoying, I understand, but it is what it is. Let's just do it quickly. Let's keep going. So now I'm gonna multiply 1 by something to get 1 over 3x cubed. And that thing is clearly 1 over 3x cubed. Multiply by 1, you get 1 over 3x cubed. And if you multiply 1 over 3x cubed by negative 1 over 2x squared, you get minus 1 over 6, right? x5 plus etc. And then we subtract. And what do we get? And what do we get here? That guy minus this guy is 0. Minus 1 over 30 x5 plus 1 over 6 x5 is 2 over 15 x5 plus dot dot dot, right? So what's that last guy? What's this last guy here? Remember, I want the first 3 non-zero terms and the Maclaurin series expansion. This is the Maclaurin series expansion, the division based on that theorem I just talked about. Multiply 1 by that guy to get it, right? So plus 2 over 15 x to the power 5, right? Plus dot dot dot. Okay, I care less here what happens. These are the guys. So it follows that tangent x is equal to x plus 1 over 3x cubed plus 2 over 15 x5 plus etc. And this is for sufficiently small x. That x actually can be anywhere between minus pi over 2 and pi over 2. Okay, you don't have to prove that, but I'm just telling you that the radius of convergence for tangent is pi over 2. Okay, all right. So this completes 11, example 11. This was part 2 of 11. Last problem is example 12. Use series to evaluate this limit. This is of the form 0 over 0, which is an indeterminate form, and L'Hopital can handle this, right? But they asked us to find it through series. So it's very similar to example 10. The question is, what's the, at the time we use the Maclaurin series expansion for EX, here what's the Maclaurin series tangent? Because we need Maclaurin series because we're talking about x being close to 0, right? So we just found it in part 2. What did we find? I'll leave it as an exercise, but let me just at least talk about it. So tangent of x, what did we find to be? The Maclaurin series, we found it to be x plus 1/3 x cubed plus what? 2 over 15? 2 over 15 x to the power 5 plus so on, right? Okay, so this is tangent of x. Again, this is the same thing as before. We're gonna subtract x from tangent. So we're gonna subtract x from the power series, and that series then is gonna start at 1/3, right? So 1/3 x cubed plus 2 over 15 x to the power 5 plus etc. This would be the numerator, and then the denominator x cubed. And if you divide this difference, tangent x minus x, by x cubed, remember tangent x minus x starts here, right, at 1/3 x cubed. So after you simplify, you're gonna get 1/3 plus 2 over 15 x squared, right? If you divide by x cubed, this becomes 1/3. If you divide by x cubed, this becomes x squared. So 2 over 15 x squared, and so on. And then if you use the continuity of, as we did before in the previous example, if you use continuity of the power series at 0, then you get to evaluate that function at 0, not that function, this function divided by x cubed at 0, which is this function, and you get 1/3, right? 1/3 plus 2 over 15 times 0 plus etc. Then you're gonna get 1/3. So the answer here is 1/3. Okay. All right. So please complete the details. I mean, you have all the ingredients. Just put them together, and again, this is very similar to example 10. All right. So this is gonna complete this section.